Gresham College presents Large Telescopes and Why We Need Them by Professor Carolin Crawford.
So today's subject is large telescopes and why we need them. And in many of my talks, I've been showing really fantastic images which are collected from a whole variety of the instruments that you're going to see in this talk today. And I want to stress how important telescopes are, because we can travel round our solar system in robotic spacecraft. We can even now send humans out into space, not very far admittedly, but we have ways of finding out what's above the Earth as long as it's within our solar system. Anything beyond our solar system, we only know it's there, and we only know anything about it because of what photons of light happen to fall our way from that distant star or planet or galaxy. So, as you often hear said, light is the messenger. It's only through the light that we have any hope of knowing what's out there and understanding it. So, the whole of astronomy, you could consider it quite a passive science. In some ways, obviously, we can run simulations on our computer, but we can't grow universes in a lab and change the initial conditions or study them. We have to just perfect the art of collecting and trapping what photons happen to fall on the Earth, and then we have them ready for analysis. And there are two problems with this. If you're dealing with things in space, they're obviously very, very far away, which makes them very, very faint and very, very small. So the whole of a telescope's job is to make them brighter and make them bigger. So that's the essential thing. You want to gather as many photons as you can, and then you want a nice crisp image that you can resolve and see details on. Now, obviously that's just part of the technique. You need the telescope to collect the light. I mean, this may be our standard image of an observer at an eyepiece at the end of a telescope. This was the case for many centuries, but now, of course, we've got a whole slew of instruments. So we've got electronic detectors that would both record the images, that'll split the light into a spectrum for analysis and understanding. So we have lots of instruments that can do the analysis for us and do the collection of light. We no longer have to rely on our eye. But they also can only work with the light that is actually collected. And so the telescopes remain the astronomer's primary tool, the most important thing that determines whether or not we detect things and which things we detect out there in the universe. And with a different design of telescopes and detectors, of course, we can extend our studies not just to the visible waveband, but also to radio, to X-rays, to infrared. Now, today's talk is going to just concentrate on the visible waveband. I found there was more than enough to talk about within sort of 50 minutes on just that subject, but I will be returning to other lights and how we collect it in future Gresham talks. So we're going to deal with telescopes and how we use them, and particularly why astronomers are always saying they need bigger, better telescopes. They're not just being greedy, there are very good reasons behind it. So telescopes were invented in 1608. The usual credit is to the Dutch optician Hans Lippershey. And the person who revolutionized astronomy by using them for the first time to look at the heavens was, of course, Galileo, who was celebrated a couple of years ago in the International Year of Astronomy, which marked 400 years since he first used a telescope as an astronomical device. And this represented the first new astronomical data in thousands of years that was available to people. His studies were revolutionary, as I say. He looked at the moon. He could see that there were mountains and craters on the moon. It had an uneven, it had a rugged surface. It wasn't perfect. It was another planet like the Earth. His studies of Venus and the moons around Jupiter helped convince him that the planets move in orbit around the sun and not round the Earth. And as I've mentioned in previous talks this year, his observations of sunspots on the sun demonstrated that the sun rotated every 28 days. And also he saw strange elongations to either side of Saturn. He thought there was something weird about Saturn that was later resolved into the rings that encircle it. He turned his telescope to the Milky Way. This no longer looked like a diffuse band across the sky through his telescope, but it resolved itself into a whole host of tiny stars. And this is the interesting point. He realised that there were many more stars out there, and in addition, when he looked at stars through a telescope, they still appeared point-like, they still appeared like stars, suggesting that they were even further away than had been previously thought. But the most interesting philosophical point about his observations was that he discovered there were new stars out there. Stars that were completely unknown about. They were objects completely invisible unless you looked at them through a telescope. And he demonstrated this by looking at well-known asterisms. So, say, for example, the Pleiades, the Seven Sisters. This is Galileo's drawing through a telescope of this little asterism, this little group of stars. Now, here's a modern photo through a telescope, just so you can spot the difference. Okay? And what he's done is the ones that are visible to the unaided eye, he's outlined with this sort of star-like shape. And every other object on here are the new stars that he'd discovered. And similarly, here is his drawing of the part of the constellation of Orion. These three are the three stars in Orion's belt, and all of these are the new stars that he discovered. Strangely enough, he doesn't include the Great Orion Nebula down in this drawing, which is quite strange. It should be there, and he didn't seem to recognise that gas and dust as something that he should include. So this is the point where you discover if you look through the sky with look through a telescope at the sky, you find new objects, and not just that, you find many more of them. There are vastly many more faint objects than there are bright objects, and so there are new worlds to explore, new things to discover about the universe if you start using a telescope. And that's when the use of telescopes for astronomy really took off. So, just to explain the principles behind a simple telescope like the one that Galileo used, it's called a refracting telescope because it uses the principle of refraction. Now, this is something I'm sure we all encountered in school, secondary school, perhaps part of your physics O-level. It's something we see in everyday life. You know, maybe not everybody sticks a crayon and a glass of water to observe this in everyday life, but you know, if you're drinking through a tumbler, drinking through the bottom of a wine glass, you see how the light is distorted and bent as it travels through some other material than air. And this is the crucial thing, because light travels at 300,000 kilometers per second within a vacuum. As soon as it starts going through a denser substance, so like water, like air, it slows right down. So a light beam passing from a vacuum to a glass slab slows by about a third. You don't see any effect if it hits the glass straight on. It just keeps going straight in the same direction. There is, however, an interesting effect if the light comes in at an angle to the slab. This slowing of the light turns the light around and changes its direction. It turns it more to the perpendicular to the glass, like here. And this is what's known as refraction. And it happens, this slowing thing, just to try and briefly demonstrate. Light is a whole series of wave fronts. Remember, it's got a wave nature, wave fronts that are all parallel, sort of perpendicular to the direction it's moving in. So perhaps cast them like this. When this wavefront, these are all travelling at 300,000 kilometres per second, when this wavefront here starts to hit the glass, this end of it slows and this end of it carries on going fast. Think of it like a tractor. Tractor's trundling along the road and it turns into a ploughed field at an angle. The wheel that hits the ploughed field slows down immediately, but the other one's travelling fast still. And what happens is you get a turning effect. This keeps travelling fast, this slows down, and the whole light ray turns until this is now in the ploughed field, or the glass slab, and then that carries on at the same speed. And the whole effect is the light has changed direction. So if light travels through a parallel glass slab, it'll come in at one direction and then turn, and then you get an equal and opposite bending on the other side, and it turns again. And so it continues with an offset in the direction it started out in. Okay, so that's not much more use for telescopes. What does get interesting is if this is no longer a flat surface, but a nice curved surface. Because you get the same effect, you get the same bending of light, but it no longer sends the light in the same direction. It actually changes the direction of the light. Now, again, you see this. This is the distortion from the bottom of the beer glass, the tumble of the wine glass. Why it's particularly exciting and useful for telescopes is if you have an absolutely perfect convex lens, all those light rays get brought to a focus. So here's your parallel slab. The light comes in, gets bent, carries on the same way. Here, parallel beams of light come in, get refracted, and brought to a clear point. And this is what we use for a refracting telescope. And this distance between the centre of the lens and where it's brought to a focus is called the focal length. And that's a defining feature of basically how long your telescope's got to be, because you've got to encounter a lens and you've got to have a point where there's a nice concentration of light. So flipping that round on its side, here's the light coming in from the left, gets brought to a focus and then carries on. And the thing is that you could put your eye there and you would have a beautiful image of whatever source is sending the light. That's all it is. And it's a much brighter image because all the light rays that have fallen on that lens have got brought to this point. So the image has been made brighter. However, it is still tiny. So the other ingredient for something like Galileo's lens is you need to make that image bigger, remember? So we include a magnifying glass, effectively, just to make the image brighter. So if you have distant light rays from something like a star, they're brought to an image of a star at that point. If you're looking at something that's an extended source of light, like the moon, you get an extended image there. And you can see the image beautifully. And it's all within what's called the focal plane, this distance. It's all brought to a nice focus there. And that's all there is really to a refracting telescope. You have the objective, which is the really big lens that gathers all the light, and you have the eyepiece that collects and magnifies the light. And all Galileo's telescope was an eyepiece at one end, magnifying glass at one end, held together with kind of two shells of wood, held together with a rubber band, sorry. That would be exciting, wouldn't it? Yeah, much more interesting than the telescope discovery of rubber in 1608. With copper bands around the outside of the wooden tube. And just very simple handheld device. Now, other features of a telescope that tell you how good it is really is things like the size of this big lens where the light is collected. That's called the aperture. And that is the key thing that tells you how much light a telescope can collect. And you will find it's such an important feature of a telescope that it comes into their names. You will often hear of pictures taken with the 200-inch Palomar, the 2.4-metre INT, the 4.2 WHT. It becomes part of a telescope's moniker. It also dates the telescope, because obviously the older ones, they're always described in inches, and then after about 1980s, they're discovered in metres as well. So I've got a little conversion chart. I'll try and give you both, but at some point I will slip into the old habit of what their normal name is. So here you have two features of a telescope that are important. The one is the size of the thing that's gathering all the light, the lens. Now, a little bit of physics, very simple physics. A larger area collects more light. You don't need to imagine in the current weather we've been having, but if you go outside and you leave a bucket and a thimble outside in the rain, the bucket's going to catch more rain than the thimble does. Same principle with telescopes. We call them light buckets. If you have a larger area, you collect more of the photons that come your way. So the bigger the telescope, the bigger the area of the lens, more photons you collect at the focus. And so this is the first impetus for getting large telescopes. You have a larger diameter lens. It just goes as the area, pi r squared. So if that's the diameter, pi d over 2 squared. So for example, Galileo's lens was about 3 centimetres across. So we've got a refractor at the Institute of Astronomy. It's a 12-inch diameter lens, that's 30 centimetres. The width is 10 times more. It's got 100 times the light-gathering power of Galileo's telescope. Fast forward to some of the biggest telescopes today, like the Keck, 10-metre mirror across, and I'll get into why it's a mirror than a lens in a minute. But that's got 4 million times the light-gathering power of the unaided eye. So you can imagine we are seeing much, much fainter objects. And of course, for astronomers, fainter objects are usually further away. which means they are also perhaps back in time. So we're seeing the light, it left them when the universe was at a much earlier age. So we start to get to much more interesting targets the fainter we can see. So the light gathering power is important. So that's how much light you get, how brighter you make things. The other thing to bear in mind is the magnification. For those of you who are interested in optics, that's just more or less the ratio of that focal length of the main lens over the focal length of the eyepiece. So if you've got one big lens, you can change the magnification by changing the eyepiece. But you can see the larger the aperture, it tends to go that it has a longer focal length, and you start to get better magnification. And magnification means the image looks bigger, you can see distinct details on it. And this is another driver. The bigger the image, the more clearly you can see features, whether it's in, stars within a galaxy or the Great Red Spot and bands on Jupiter. All of those increase with your magnification up to a point. So, and just to go back to Galileo's telescope, the magnification that was only 20 times, but 20 times magnification was enough to completely change his view of so many things, start to resolve those individual features in the Milky Way and on the Moon. Of course, lenses have their problems. I mean, this really took off, this new design, and astronomers started to use it throughout the 17th century. You have a couple of problems. One is that there's the tiniest flaw in the lens, tiniest little bubble, little flaw. The light path gets disturbed, it gets slight distortions, and it's not perfect. So really perfect convex lenses, very expensive. So telescopes were expensive. The other thing is a slight problem with the lens in particular. If you pass white light through a glass prism, it gets dispersed into rainbow. That's also a problem for astronomers using these lenses. If you send white light, even though that looks kind of greyish, but white light into the lens, the blue and the red lights are brought to a slightly different focus. So if you were to look at an uncorrected convex lens like this, you would get a little point of light and then this kind of rainbow halo around it. And so that's not very good for observations, obviously. And so one of the corrections is that you can't just have a convex lens, you then have to have a corrector. This is called a chromatic aberration. So, problems with the colour. You have to more or less fuse a second lens onto the outside that makes a correction for this. And again, that kind of pushes the technology a bit as to getting a really good lens. But nonetheless, refractors were the telescopes of choice for decades. You start off with Galileo's refractor, and another example, I talked about the Northumberland 12-inch refractor in Cambridge. It dates from 1838. Here you see us all this is what we do. We wander around and pontificate in our mortarboards and gowns in Cambridge. Not really. But in here, just poking through, is a 12-inch refractor. This is what it looks like now. And this is where you begin to see one problem with refractors apart from the lenses, so they are long. The bigger the lens, the longer the focal length, the longer the telescope has to be, and hence the building the telescope actually has to be in. So for a 12-inch lens, so 30 centimetres, 1 foot wide, the whole tube here has to be 19.5 feet long. You can't just go on getting bigger and bigger lenses. It gives you more light gathering power, but you get an increasingly unwieldy telescope. This carries on until you get to probably what's the last, well, it is the last and the biggest refractor. And that was built in 1897 at Yerkes Observatory near Chicago. And this is a fantastic beast. It's enormous structure there. Okay, that whole tube is 19.5 meters long. Those of you in the front row might recognize this guy just here. And this is a current picture of it today. This is an enormous structure. You can imagine it's so heavy. The whole tube weighs 5 tons. The lens alone, so the lens is 40 inches across, so that's 102 centimetres, just over a metre. Here's a picture of it. That alone weighs 450 kilos. And this is the limit, really, where you can't build refractors any bigger. The lens has to be unobscured, so it's just supported round the edge within the tube. You get a bigger lens than this, it'll start to sag and deform under its own weight, under gravity, and that will distort the light paths through the lens. And to actually build bigger lenses than this gets nearby impossible. And also the length of the tube and the weight of the tube get quite monstrous. So this is the end of the line for refractors. And it was about this point that at the end of the 19th century, the beginning of the 20th century, that reflecting telescopes were the ones of choice. So again, this is a very simple idea. It doesn't do refraction through a lens, but you're talking reflection from a slightly concave mirror. Parallel beams come in, and they're brought to a beautiful, well, okay, it's not always this beautiful, but brought to a focus here. Now, this was realized in 1663, so 15 years old after Galileo started using refracting telescopes by James Gregory. But he had this idea that you could bring light to a focus using a mirror rather than a lens. Great idea, apart from there's a fundamental flaw. Here's where the focus is. That's where you would you put your eye to look at the image. You put your eye there, you block the incoming light. You're in the way of the incoming light. And he didn't see a way of getting around this. So even though it was an idea, it doesn't put into practical use until Newton came up with the idea, well, what you do is you just stick a little mirror in there and you fold the light out. You redirect it through 90 degrees out of the telescope. You put your eyepiece here and you can observe. So this is the Newtonian design. This is your classic reflector. If you've seen the replicas of Isaac Newton's telescopes, either online or places like the Royal Society, here's a replica, I think, of a second telescope. Light comes in here, bounces off the mirror end, bounces off what's known as the secondary mirror there, and out, and the observer views through the eyepiece there. So you've got the same principle. The bigger the mirror, okay, the more light you collect. You also have other advantages. You can make the mirror so that the focal length isn't as long as a refracting telescope, so the tube is shorter. Also because the way that you're folding up the light. So if to go from the lens to the focal point is that long, if you have a mirror, the light comes in and then it's folded up within the tube, and the tube can be shorter and stubbier and not such an unwieldy beast. Mirrors do have problems, but you don't have to worry about expensive glass lenses as well. So it's a different solution to the same problem. And indeed, Newtonian reflectors are still quite common today. If some of you may be amateur astronomers, there are reflectors such as this. This is a Newtonian reflector. Light comes in, bounces off the mirror, deflected at another mirror there, and there's the eyepiece, which is fine if you're using your eye. The minute you want to stick a collection device for the light, such as a camera, or maybe you want to split the light in a spectrograph, it starts to get a bit of a problem that this is right at the business end of the telescope tube. You're going to unbalance it. And even with your eye, the bigger the telescope, you're still going to have a longer tube for a wider telescope, the more inaccessible that eyepiece is. So this design, it's great up to a point, but it's no good for the large telescopes we're talking about today. So there's another refinement, which is actually a very smart one, due to Laurent Cassegrain, who was a contemporary of Newton's from France. And what he did is, instead of sending the light out to the side, he introduced another mirror in the middle, another secondary, but instead of being inclined at 45 degrees, this is now flat. And what that does is it sends the light comes in, bounces off the primary, bounces off the secondary, and I've drawn it flat, but in fact it's slightly convex, so you can increase the focal length if need be for the telescope, and the light comes out through a hole in the first mirror, okay? Which is really nice for lots of reasons. Again, you're folding up the light more so the tube is smaller, and again, this is a design that's used on a lot of amateur telescopes. Here's an example where the light comes in and the eyepiece is on the end here. Now, of course, this means your primary telescope has to have a hole in it. And that's true for even modern telescopes. Here's the WHT, so this is 4.2 meters across odd, and you can see this giant hole in the middle, so the light can pass out through the back. What you lose in this design, obviously, is you don't get all the light from the telescope down the middle. This isn't to scale, but there is a little bit of light that gets obscured. You get a slight loss of light in terms of the light gathering power, but nonetheless it's a very good design, and it is the one that all modern telescopes use, because if you want to put a camera on the end, you can do this very easily. Here, for example, is the Isaac Newton telescope in La Palma. This is the business end of the telescope. If you had a Newtonian reflector, you would want to have all these gubbins up at this end. You can't do that easily, totally unbalanced. But it's much more convenient to pipe the light out the end of the telescope, and then you can redirect into a whole host of instruments that hang off the telescope like a sort of Christmas tree down here. So this is all the instrumentation, very solid, good place to have it within the telescope. And there are other advantages to this design. Again, let's just show you the Isaac Newton from a slightly different angle. You can see all the instruments down here. You maybe be able to see their instruments up here. This means that you can do a couple of clever things. You can retain it as a Cassegrain, but most modern reflectors, you can have a means by which you can then insert perhaps a third mirror. Sorry, no, I'm going ahead of myself, right. You can remove that mirror, and you can still use this prime focus. And you could put a camera or a CCD collector just right at that focus and still get that position. So you can have a whole lot of instruments on the bottom, then you can have another instrument at the top, and you just need to remove the mirror that divides the light between the two. And there are a whole host of reasons why this is a much better place to look and to collect your images. You get a much sort of wider field of view, so you see more of the sky there. And not only that, the light's only been reflected once, and so you haven't lost much of the light at all. You get the crisper images, larger images. It's the best place to take images in a telescope if you can, which is not always easy, okay? Obviously, nowadays we have remotely controlled CCD cameras up there that can collect the light for us. You just put a little one in, it collects the light. Hasn't always been the case. Certainly the last part of the 20th century, film and photography was very much in use, which means somebody needs to be there to change the photographic plate every 30 or 40 minutes. So many of the telescopes will have an observer's cage at the prime focus. So this is the 200-inch Palomar, and you can see that there's the main mirror, and this is where the prime focus is, or you can have the secondary mirror again, which redirects the light. And this guy is actually sitting there, ready to do the observation. So you had to have an observer sitting in the prime cage through the night as the telescope slews across the sky and observes something, and they're changing the photographic plates. And here's the elevator to get into the end of the tube. There's also one at the Anglo-Australian Telescope near Siding Springs, and again you can see the long tube-like observer's cage, and here's an observer sitting with the camera in that tube. This was still very much active in the 1980s, and I know very many of my colleagues. So if you had an observing run at the AET, the greatest thing at all is if you managed to get a ride in the prime focus cage. Yeah. Best thing of all. I never managed it myself, but several of my colleagues did. Great experience now. Sadly, not actually necessary, but nonetheless, it's a nice idea. And of course, you've got to realise that as the telescope slews from one side of the sky to another, you could end up hanging upside down. So you have to have a chair that kind of swivels round so that you always... So even the mechanics of how the observer sits in the prime cage is quite interesting. So you've got that as an option. And of course, there are lots of other refinements of this. You've got your Cassegrain focus, you've got your prime focus. Another thing that's even cleverer, because imagine you've got a really big instrument. It's far too heavy to hang on the end of the telescope, and I'm afraid the more light you collect, the more ambitious astronomers get with what they're going to do with the light. They need bigger and better instruments, heavier instruments. And it's not practical to have them all hanging on the end of the telescope. So you can introduce a third mirror, a tertiary mirror, that comes in and deflects the light off to one side. So this is called either a coude, which is the French for bent like an elbow, so I think it's a good name for it, or Naismith focus. It depends on the telescope mount. And you could do it that way. You could then put another mirror in and turn the light that way. And the advantage of this is you can have instruments that aren't anchored to the back of the telescope, but they sit to either side of the telescope. Here's the WHT, William Herschel Telescope, 4-metre telescope in La Palma. There's the telescope prime focus. You've got instruments down here at the Cassegrain focus. But you also, these huge boxes here sit on platforms. These platforms are part of the structure of the telescope that rotates. So they're not actually hanging off the telescope, but they move kind of around with it. But you can have enormous, bulky instruments, ones that people can wander around in, that operate on the light from the telescope, and they're nicely and safe on these Naismith platforms to either side of the telescope. So again, a huge practical design. And nearly all of today's large reflectors use, well, all today's large telescopes are reflectors that use this design. There are disadvantages, of course. I've already said, when you put your secondary mirror in, you lose a bit of the light that's going to land on the mirror. And another thing that you may not have thought about, but it also introduces artifacts in your image. We're so used to seeing astronomical images that, of course, what we expect to see are these crosses that surround the bright stars. These are known as diffraction spikes, and they're due to the fact that the secondary mirror can't just kind of hover there unsupported above the primary mirror. It has struts to either side. You can see it perhaps in these images. This big one has struts. Even modern day reflectors have these struts. And they block the light, and it's diffraction, the way that light spreads round an obstacle. Basically, incoming light is scattered round and spread round these support struts. And the light from a bright star gets scattered to form that diffraction spike, that cross shape. And it's just due to the struts holding the secondary in place. It's not a problem. You don't see it with refractors, obviously, and you don't see it through if you take pictures through a refractor or without a telescope at all. It's just an artifact of these reflecting telescopes. And they do tend to be a bit of a bane for astronomers. You can always warrant, if you've got a really, really interesting faint galaxy, it's always going to lie right under the diffraction spike, of a bright star. It's always the way. The most interesting thing you find is always hidden right under there, and you have to go back and re-observe it with a different orientation. So that is something that's introduced. But there are a whole host of advantages, as I say, about mirrors. So mirrors came into the fore, really, in the 18th century. There were refinements to the shape. You've got the original reflecting telescopes used a spherical mirror, but they weren't perfect. It doesn't bring everything to that nice, neat focus that you need for a single image. It kind of brings everything to a bit of a mishmash of an image, and you kind of get your best place to put the focus, but not all the light is focused. So you'd look at it, and there'd be a bright star, and you've got this sort of fuzzy halo around it. So instead, it was discovered that a slightly parabolic, so this is a slightly deeper curve, produces a much better focus. Of course, these are a lot more difficult to grind. A spherical shape is very easy to measure. Parabolic shape is slightly deeper in the middle, and they prove very difficult to to bend metal or to mold metal into that shape. Indeed, this parabolic design is incredibly difficult. I mean, it's hard enough to sort out when they were building telescopes reflecting telescopes like this in the 17th century. It was also hard in the late 20th century to get it completely right. As some of you know, the Hubble Space Telescope, there was an error in the shape of the primary mirror, 2.4 meters across, 2 microns, so 2 micrometers, too flat at the edges. Enough to have absolutely catastrophic effects for the image. Here's what they saw when they went up. Most of the light's brought to focus, but the light just from the edges of the mirror doesn't quite get to that focus. It overshoots, and you get all this scattered light right from the outside of the telescope. And this wasn't repaired until a while afterwards, and it was an astronaut servicing mission to the Hubble Space Telescope. They put in something called COSTAR, which starts with correcting optics, and I forget the rest of the acronym. But it needed no less than something like 5 pairs of mirrors to correct for this error in the shape of the primary mirror. So it's not, it isn't trivial, obviously, even with the best of what NASA has to provide at your disposal. So these reflecting mirrors took off. There was one very famous one. This was the Herschel one. It was built by William Herschel. So discoverer of Uranus, discoverer of the infrared radiation, for example. This was more or less finished in 1789. And it's got a 40-inch diameter mirror, so that's 120 centimetres, so 1 metre 20. And the whole tube now is 12 metres long. So considering you've got a much wider collecting area, the tube's much shorter, say, than that 40-inch refractor at Yerkes. And you can see the whole thing is mounted on this sort of trellis, and the whole trellis can rotate. There's a turnable mount here. It is said that Herschel's first observation with the telescope was before it was finished. And it was made by him basically a couple of years before it was finished, crawling down the tube with a handheld magnifying glass until he found the focus. And then he could observe the Orion's Nebula. I mean, that's what I call an enthusiast, right? Crawling inside a telescope to find the focus. And this telescope's so famous, it's part of the Randall from the Royal Astronomical Society here. And quicquid notandum means something like whatever shines should be observed, which is a very good motto for any astronomer. So this was the largest telescope in the world for a long while. It wasn't desperately successful, partly because it's in Slough. You can't imagine the weather was very good in Slough. He only used it till about 1815. He had problems with the mirrors. I'll talk about the mirrors in a minute. So it wasn't the best, most successful telescope, but it was a fantastic prototype, and he did discover a lot with it. But it was surpassed in 1845 by something called the Leviathan of Burcastle. Fantastic structure. Now, this is a mirror which is 183 centimetres across, so 1 metre 80 across. Enormous structure. The whole tube and the mirror weighs 12 tonnes. So it had to be supported by these thick walls on either side, which meant the telescope couldn't move very much that way. It could only move in this way. So it's only limited to seeing things when they cross over the zenith overhead. But nonetheless, the data he collected were fantastic. Now, remember, this is before cameras. This is before, obviously before electronic devices. All he's using is his eye. And yet, Lord Rosse, the guy on the left here, who designed and built this fantastic telescope, he did observations, fantastic drawings like this, perhaps, of the spiral nebulae. And this is what he wanted to study with his telescope. He wanted to look at these faint, fuzzy nebulae. And he determined that some of them have this spiral structure. And the other discoveries like this, some of them contain points of, bright stars within them. This is his observation of the Whirlpool galaxy. Just compare that with the modern-day Hubble Space Telescope image. And I think he obviously had much better eyesight than I have, but obviously a very good eye for detail in his drawings. And he did fantastic drawings of a whole host of nebulae and what we now know as spiral galaxies. So both Herschel and Rosse built their mirrors out of metal, something called speculum, which is an alloy of copper and tin. In fact, here's one of Herschel's mirrors. You can actually go and see this in the Science Museum for that telescope. And there are problems. This alloy is called speculum. It kind of goes to a white metal, and you then have to polish it to get it shiny. And there are problems in that it's quite brittle. Even as you polish it, it can break, which is not good. You can shape it beautifully, and you can make the mirror large, but also there are problems that it can deform, especially due to temperature changes, like if the night's cooling down, and that can distort the shape and the way that the light is brought to a focus, and it tarnishes very quickly in the open air. Herschel had to have two mirrors, so one's always being repolished, ready to replace the one in the telescope. He's forever swapping them in and out, and this is one of his spares from that telescope. And the other thing is it's not actually very reflective. You lose about a third of the light that falls on the mirror, so it's not the best design. And so again, these mirrors took a while to take off in their use, this idea of a reflecting telescope. The other thing, of course, is they get larger, they get heavier. Like Ross's mirror had to be supported by braces on the bottom just to keep its shape. So the next major advance was using glass. And here, all the problems reflecting mirrors went away. If you have a glass slab that you then grind, you sort of continually grind the glass and you smooth it into a hollow, and then you get the perfect shape. And then you coat it with silver. So this breakthrough was the idea of chemical deposition. It happened in the late part of the 19th century, where you can actually use, you can just have silver deposited as a very thin layer over the glass. You get your perfect mirror. And this is when reflecting telescopes really took off. First of all, mirror reflects 90% of the light, silver reflects 90% of the light that falls in it, much better than the speculum metal. You can do the glass to a very fine, you can grind it very, very well, you can shape it better than you can the metal. You can recoat it, even though silver doesn't tarnish as much as the speculum. It all becomes a much more useful material altogether. And from then on, all reflecting mirrors and telescopes were made using these glass blanks that are then coated with silver. This means things like they're quite cheap. The glass doesn't have to be perfect like it does with refracting lenses. Any bubbles or flaws in the glass aren't important, okay, because they're all covered over by the reflecting substance. So it's much more practical. And so you have a new generation of telescopes. Starting with the ones at Mount Wilson, you've got the 60-inch here, so it's 60-inch reflector, and you've got the 100-inch, so that's 152 centimetres and 250 centimetres. These were at Mount Wilson Observatory north of LA. Fantastic images, real workhorses at the early part of the 20th century. It's this telescope with which Hubble discovered that, these little spiral nebulae that Ross was looking at are galaxies outside our own. This is the telescope he used to discover that the universe is expanding. A lot of seminal discoveries with this telescope. And this was the largest telescope right until 1948, when the famous Palomar telescope was built. 5-metre diameter lens at the bottom. Look at the size of that. There we are. Isn't that a beauty? So 5-metre diameter mirror at the bottom. And this was the largest telescope in the world. Certainly all the time I was growing up, it was the really famous, the biggest telescope in the world. And it stayed that way for like 45 years. And then things changed. We have new telescopes come along. So modern large refractors include sort of like the Gemini. There's one in Hawaii in the north. Well, you may not think of Hawaii as the north, but it is. Hawaii in the north, Chile in the south, both 8 meters in diameter. You've got the twin Keck telescopes, 10 meters diameter mirrors as well. You've got the large binocular telescope, 2 8.4 meter telescopes side by side. You could combine the light, and it's as if you've got a giant, almost like 12-meter telescope that you can use the light from. And of course, a very famous, very large telescope down in Chile, VLT, where you have 4 8-meter telescopes, which can be used individually, or the light from all of them combined to mimic a bigger telescope. And then the biggest telescope at the minute, this is the Grantican. It's a kind of fisheye lens, so it's a bit difficult to make out the structure, but here's the prime focus, and here you've got a 10.4 meter mirror. This is the kind of instruments we use now, and they're all that same basic design, but they're bigger and better. And what various ways that that's happened are differences in perhaps the manufacture of the mirrors. Up until the 1980s, the mirrors were always made out of those glass slabs. And that means there was a limit as to how big they could be. So telescopes built like the ones on the Palmer, the Isaac Newton telescope, the William Herschel telescope, use these really thick mirrors, which is fine up to a point, but then they get really heavy and they distort as they go up. As the telescope slews, they'll distort under gravity because there's still glass underpinning it. It also makes it very difficult to move a heavy telescope around. So all these new telescopes now have developed technology where they have much, much thinner mirrors. So something like the WHT, the width of the mirror at the centre is 15% the diameter. Something like the VLT, it's about 2% of the diameter. So this is one of the VLT mirrors being polished. Much finer precision. This also means the mirrors are a little bit flexible, so you can cheat. As they slew around the sky, gravity will still affect them. They'll still respond to changes in the temperature. But these are things which are predictable. You can compute them. And underneath the mirror, they have a bed of little mechanical devices called actuators. This is what one of the mirrors sits on. And it can just subtly change and compensate for any deformations and distortions in the shape of the mirror. By computer, it can just correct for them. Very smart. So that's called active optics. And it's what we can do to enhance the shape of the whole mirror and make it absolutely perfect all the time. And beyond that, we also use segmented mirrors now. Again, you want to build bigger telescopes. You're reaching the limit of how big a telescope you can, one single blank you can get. So I talked about the Keck telescopes, the Grant-Can telescope. They don't just use one big mirror, but they use segments of individual mirrors. So this, for example, is the Keck, and you can see, well, maybe you can't see, but they're sort of hexagonal tiles mimicking one larger surface. And underneath all those tiles, again, you have these actuators that can tilt them and just change those individual mirrors. This is the Grant-Can. Here are some of the mirror segments. Here's the mechanical things underneath that are just subtly altering that tilt. I mean, of course, these segmented mirrors do come with problems in that you do have refraction effects about those gaps between the mirrors you have to worry about. But it enables you to get much bigger telescopes, much bigger mirrors. So you would think that's all there is to it. You just build bigger and bigger telescopes, you get a much better light collecting power, you also get better magnification. That's fine up to a point, because there comes a point where, however much you magnify the image, you can't make out details because there is this problem of what's called a seeing. There's microturbulence in the air. The air is moving around all the time. Light travelling through air that's moving, you get continual refraction problems. This is why stars twinkle. And if you look at something like Sirius, where you see it through a lot of the atmosphere, it sparkles and flashes. It just affects the light. So if you're collecting the light from one star for a long time, that light all blurs out. And you can magnify it all you want, but all the detail on it is completely blurred. So there is a problem of seeing. So with big telescopes, you get better theoretical, what we call resolving power. And this is affected by the seeing. So imagine there's no atmosphere and you build a bigger telescope. What we call resolving power is how far apart two things are that you can resolve them as two individual stars rather than one big blob like that. So if you want to do the mechanics of what the angle is between those stars, it's a number times the wavelength over the diameter of the telescope. So again, bigger the diameter of the telescope, the smaller the resolving power, the closer things can be resolved or be made separate. So a big telescope is really good, and you have this theoretical limit for any size of a telescope. That's only achieved if you're out in space, where there's no atmosphere in the way. You have the problem of the atmosphere blurring all this, and we try and get down to the best that the telescope can do by crafty means. You have to monitor what the seeing is, what this turbulence is in the sky, so you can then correct for it. And so you not only just have the active optics, where you're changing the shape of the mirror in response to temperature changes and gravity changes the telescope slews around the sky, you've got to do something which is called adaptive optics, which is responding to a situation, responding to how much the atmosphere is moving around and how much is twinkling. So obviously the best adaptive optics is you put your telescope in space and you don't have to worry about the atmosphere. The next thing you might do is you put your telescopes somewhere where there isn't so much atmosphere. So here's a picture from the aeroplane as you come into Mauna Kea in Hawaii. Hope you can all see the telescopes, yes? They're up there. There we are. They're all perched right in the rim. So that's 14,000 feet up the mountain. And that's fantastic, because you're above the warmer, the thicker part of the air, and you're just looking through a much thinner part of the air. I mean, there are lots of reasons why it's good for things like infrared astronomy, and it's good for the weather, and that you're mostly above the clouds, but also you're looking through the cooler part of the atmosphere that's moving around less, and the thinner part of the atmosphere, and so there's less of the twinkle. So that's one of the reasons you put telescopes in these high mountains, is to reduce that blurring. But you can also do it by looking at a bright star. So imagine I've got a really faint galaxy I want to observe, and I want to see tiny details on it, and I need a really crisp image. Well, what I do, if there's a bright star nearby, what I can do is I can monitor that star all the time, and I know what it should like as a perfect point source if the atmosphere wasn't there, and I can measure continually, however many times a second, how that shape changes and distorts. And therefore, I know what correction I can make to my mirror to compensate for that distortion. And then as I do that, I'll get a much clearer image. I'm taking the telescope down to this theoretical best resolution it can have. However, the problem is, whatever fantastically interesting source you want to see in the sky, it's never close to a bright star. Okay, this is the opposite of the diffraction spikes. Now, when you want something you want to see really clearly, there's no bright star to be found anywhere near enough. And it has to be bright to be able to get that enough signal in to monitor how much the light is changing, the blurring is changing due to the atmosphere. And in fact, there's only about 10% of the sky that's close enough to bright enough stars to be able to do that kind of active optics. That is one way we compensate for it. Another thing that many telescopes do, such as the 4 VLT telescopes, is they create a star for you. So no, they don't do a supernova somewhere, but they have a laser beam that comes out of the prime focus, so it's directly lined along the direction to the bit of sky you're seeing. And this laser beam creates an artificial star, probably about 90, 100 kilometers up in the sodium layer of the atmosphere, but high enough up that you then view that star through the atmospheric turbulence. And so by monitoring the shape of that artificial star, you can create a bright star close to your source, do the active optics to respond to the blurring of the atmosphere, and then correct for it. And again, you would still use all these actuators underneath the mirror. So you can see it's not a case of just bigger, larger telescopes. It's also working out how to make them perform to their very best specs. And all the modern telescopes will have active optics. They'll have adaptive optics. This, as much science goes into understanding those and making that as to actually building mechanically the biggest telescopes. So where are we now? This is the current suite of instruments. 8 meters to 10.4 meter diameter mirrors. These are the ones that I and all the other astronomers compete to use, the state-of-the-art instruments if you are, you work in the visible waveband. There are promises of much better, bigger telescopes to come. It's not just that we're greedy, but just remember, the bigger the telescope, the fainter you can see. That means you can start to perhaps see light from planets orbiting around other stars. You can look at individual stars and structure within distant spiral galaxies. And of course, the more gathering light power you have, the fainter you see, the further back in time. We really, really want to see the faintest objects, the furthest objects, and perhaps the ones where first stars, first galaxies are forming. And for that, you need bigger telescopes. So there are lots of science drivers, of course, behind these. And there are some fantastic telescopes on the way. Now, these are artist impressions, I do want to stress, okay? These are not built yet. So here are like the 3 main contenders coming up. You've got the giant Magellan telescope. This is going to have 7 mirrors sort of arranged in a sort of, well, you've kind of got a hexagonal array of them around the middle one. Each of those mirrors is 8.4 meters across. So the whole thing's going to mimic 24.3 meters across. So it's going to make like a giant, one giant dish. Again, you can imagine there are going to be problems about interpreting and combining the signal between these mirrors. But this is something that has already been started. 2 of the mirrors have been cast. They even last month started blasting the top of the mountain where it's going to sit. Funding isn't entirely approved, but it's on course. They're silvering the first mirror. It's going to take a while. Or even perhaps they're still shaping the mirror. They've just cast the second mirror. They reckon probably about another decade they might begin to get the first light in it. Another alternative is the 30-meter telescope, which, as its name suggests, is going to mimic 30 meters in diameter. But again, it's not going to be one big mirror. You're looking at a hexagonal array of lots of smaller mirrors. In this case, you're going to have 492 mirrors, each 1.4 meter across. And then these are all tiled, again, to mimic one giant mirror. Fantastic idea. I mean, these are some of the ones that are less certain. The one that has only got definite funding for completion is a European telescope. Now, there was originally a case for a telescope that was called OWL, which was overwhelmingly large telescope. Unfortunately, that was just too ambitious, that whole structure, and so that's got shelved. But instead, we have the EELT, which is the European Extremely Large Telescope. But this is something that's going to be based in Chile. It's going to have a mirror 39.3 metres across. Original spec was for over 40, something like 42, but it's now got descoped slightly to 39.3 mirrors. I've got to check my stats here. That's 800 hexagonal elements, each 1.5 metres across. Okay, so fantastic technological challenge. And the idea is that this will be down with the telescopes in Chile, so observing the southern sky. And for all those mirrors, you're going to have something like 6,000 of those actuators underneath. So you can begin to see it's not just design of the telescope, it's the mechanics of making the telescope work and achieve its best and best resolution. And this is true not just for ground-based telescopes, just putting a flying mention for the next generation space telescope. It's also going to be bigger, better. I know it's strictly not an optical telescope, but just for sake of completeness, I'll just mention, if this is your Hubble Space Telescope mirror, it's only about 2.4 metres across. The James Webb one is going to be substantially bigger, about 6.5 metres across, which of course has to fit into a rocket. It's going to go out to space, okay? So you've got to imagine, you've got the technological challenges of it's going to have to be compressed and then these segments folded up to mimic the big dish. We're really going to get that right. So, you know, this is more or less, you've not just got hexagonal segments, but these have to self-assembly out in orbit. And not just in orbit, actually way out beyond the moon. So it's not somewhere, we've got to get this one right because we can't send astronauts in to rescue it and correct it if it goes wrong. So you can begin to see why this is eating up most of NASA's budget and is one of the hugest technological challenges we have coming up in new telescopes. Okay, I think that's probably enough from me about telescopes. I'll just remind you that perhaps some of you may wish to come back in about a month's time. And the subject matter will change completely, and I'll be talking about stardust, how we find it and what we learn about it, and back to some beautiful images of space. Thank you.
For all information, please visit www.gresham.ac.uk.